Alright, so today we are going to be talking about deep learning and neural networks. So basically last time we gave you guys the basic rundown of how machine learning works, but today we're going to actually talk about the math and like coding behind it. So the first thing we got to do is figure out the basic intuition behind machine learning, right? Like what does the computer want to do in order to learn from prior experience, right? For us it's pretty easy, right? We just do stuff and then somehow we like remember what we did and what went wrong and what went right. But a computer doesn't have the exact same brain structure as us, so we have to be a little bit creative here. So, let us just say that we want a computer to predict housing prices based on square foot, right? So, basically the scatter plot is like the canonical example of like machine learning, right? Like this is the first example you will see in most machine learning courses. You basically want the machine to take in a number of square feet and then give you a price, right? So, um, to begin, how would a human do it, right? How would you predict if I asked you to like find out how much a house with 5,000 square feet would cost? What would you do? What would your strategy be? Anybody? Come on, what would you do if you if I asked you to find how much a house with $5,000 cost? Come on, you guys all have taken science, okay? You guys should know. Please, somebody. Nobody? Okay, let's see. Who should we call on? Aiden Yi. You want to you want to tell me what would you do in order to find how much a 5,000 square foot home would cost?
Take the average of 1 square foot among like a bunch of houses and multiply by 5,000.
Take the average. Oh
Like
yeah,
average
so
cost.
you have a decent idea, right? So basically that would be like finding like approximately what the ratio between the square foot and the price is, and then um, using that for 5,000. But that means that a zero house, like a house with 0 square foot, would cost zero, and everything beyond it might cost more, right? But what happens if we wanted to like build something better? Like what have you guys heard of extrapolation? Like in like your science classes, how do you do extrapolation, right? Like if I tell you to do something like beyond, how do you do that? What geometric figure do you put on this graph? Anybody? Nobody has a good guess. This is actually so sad. Okay, well, I'll give it to you guys. It is putting a line of best fit, right? So essentially, Aiden's strategy is you find the slope of the line and assume that it goes through 0, 0, and that's okay, right? Like, you could do that. But essentially, the line of best fit could like not necessarily go through 0, which is why I wanted a more specific answer. But that is okay. So how would a computer do it? Well, a computer basically does the same thing, right? It basically finds a line of best fit, then just finds like, okay, 5,000, where's the point on the line? 5,000, and that's how it does it. So how does the computer actually find that line? So it's something called linear regression, and it basically chooses a line and evaluates a cost function on it, right? So that's basically how bad the line is. So can anybody tell me what a good cost function would be for a line, right? Like how do we define how bad this line is?
Like find the distance from each of the points of the line
Yeah, so
and do like the
basically
root mean squares.
yeah. Basically, a common like error thing that like a common cost function that like linear regression algorithms use is they basically take the distance from the line to the point, the vertical distance, and it squares it, and that's basically called least squares linear regression or something. I forgot. So something like that.
Least squared regression.
Yeah. Oh yeah. LSRL. Yeah. That's what it was. Least squares regression line. That's what it is. So essentially, it takes the least square. It tries to minimize the square of the distances to all the different points, and then eventually you get the best line. So the way it does that is it uses calculus, right? Like, what function would you use in order to like? Okay, so let's say you have like a parabola, right? And you're over here, right? How do you like find like how do you get to the bottom of the parabola? Does anybody like what calculus function would you use? Like,
I think
which way
the
would you have to
partial
go?
derivative.
Yeah, right. The derivative. So if your derivative is positive, right, you want to go down the slope. So the derivative is basically just a tangent line. So if you wanted to go down the slope, you would basically like go the opposite direction of the derivative. So that's basically how it uses calc in order to find the minimum of the function in order to minimize the like cost of the line. And essentially, like, you don't always have to use a line, right? Like, for example, in this thing, there's a degree 4 polynomial, right? There's an actual function. If you use a linear, like, regression on this, you get such a bad model, right? It's, like, horrible. But if you use a degree 4 model on this, it gets pretty close to actually approximating it. And if you use a degree 15, like, I mean, sure, you get a cost of like 0, but like, I mean, that is not a very good approximation of the function, right? So essentially, what we want to do as computer scientists is we want to make a flexible, complex function that can map all of these different functions, right? We could do lines, we could do quartics, we could do quintics, anything, right? But essentially, we should not have to know what the function is beforehand, right? We should just be able to chuck in some data and it will spew out a epic model. And essentially, that is what neural networks are for. So now Mason will be talking about what neural networks do.
Okay, so you go to the next slide now. Yeah, so we'll use another motivating example. And this example is recognizing handwritten digits. And it's kind of fascinating how our brains can do this because the exact pixels of each picture, like all these threes on the right, they differ, but our mind can still recognize it as a digit 3, no matter what kind of pixel arrangement, no matter what kind of differences it has. Actually, I can share screen. Roman.
Oh yeah, that would probably be better, yeah. Okay, let me stop.
Enable.
Oh yeah, that's not bad. Okay. I'll just make this actually easier.
Okay, cool. Yeah. So we can recognize any arrangement of a 3 and recognize as a digit 3. How can you write a program that does this? So that'd be pretty hard, but if you go through the 28 by 28 pixels. Now this is where neural networks come in. So we'll treat all these inputs, the 28 by 28, so that should be possible pixel values as inputs. And there's 10 possible outputs, the digits 0 through 9. And this is following what we talked about last meeting. This is a multi-layer perceptron. And I'll show you next slide. So these are the 784 inputs. This is 28 by 28. And there's 9 outputs. And this is called a multi-layer perceptron. So there's many different types of neural networks, but this is like the most basic, plain vanilla one. And the neural network consists of 2 words, neural and network. So first of all, neural. What are the neurons in a neural network? And network, how are these neurons connected? And what does that mean? So first of all, what is a neuron? I talked about this last meeting about how Perceptron by Rosenblatt in 1958 is just a single neuron, and it takes in inputs, and it has like a weighted sum, and that's the output if it's 1 if it's greater than the threshold and 0 if it's not. So you can imagine you get 3 inputs, you multiply each of them by a number and then sum them together, and then you'll get your output. So for our purposes, you can just think of a neuron as something that holds a number. So its value will be its activation. So if it's like say 1 or a high number, that's a very activated neuron. If it's 0, that's not activated. You can also think of a neuron as a function because it takes in inputs and it has an output. For now, we can think of it as a number. And in this case, we have 28. Okay, so this is what I was talking about. There are 28 by 28 inputs. Here's a neural network. Here are neurons, and here's the output layer of 10 possible outputs, but 0 through 9. Now, we want so how do we get the correct answer from this neural network? You can imagine this as a black box right now. You give it 784 inputs for the pixel values, and you'll get some kind of output. And how do we know, what do we want to happen? What we want to happen is we want the digit 9 to have a high activation. So 0.38 isn't very high, but we want this to be as high as possible, while the other neurons are all low, right? So if this was actually a handwritten like 3, we want the 3 neuron, we want the neuron corresponding to a 3 to have a high activation, while the other ones aren't activated at all. That's our goal. And these are the neurons in the output layer. Here's the input layer of 784 inputs. And here are 2 hidden layers of 15 neurons each. And that's just an arbitrary number. You have to tune and play around to find out what number of neurons or what number of hidden layers or what structure you want works the best. So again, we want the activation of the correct output to be high while the rest of them are 0 or not activated. And this is inspired by brain neurons because activations in one layer will fire certain activations in the next layer, right? Certain input activations, so some pixels are high, some pixels are low, will cause some sort of will cause certain neurons in this layer to fire, which will cause certain neurons in the next layer to fire, which will cause certain neurons in the last layer to fire, which hopefully the last layer, the certain neurons we're talking about is the correct neuron, and the rest of them are zeros. And in your brain, you can imagine you have pathways. Like say you develop a habit, neurons that fire together, wire together. This is where the saying comes from. Basically, certain neurons will cause certain next neurons to fire. So I talked about how certain neurons will fire in the next layer. And let's talk about, let me give you another example of how this might happen so it makes sense what I mean, right? So you have so we're looking at these 10 outputs here. Well, we know that we know that the activations from the previous layer will trigger the correct one in the last layer, right? So in a perfect world, let's think about what the previous layer might have. The previous layer might consist of components, right? Components of the digit. So a 9 would be made of a loop and a line, and 8 would be made of 2 loops, right? And if in this previous layer we have the correct activation, so in this case we have a 9, and over here we have the loop is activated and the line is activated. If these two are activated and nothing else is activated, then clearly it should fire the 9, right? And then if this one, if the 2 loops were activated, then it would fire the 8. So this is what I'm talking about when I say certain activations in this current layer will cause certain neurons in the next layer to activate, right? And you can imagine this problem could be broken down even further. So how do we know this is the line? How do we know to activate this? Well, the previous layer might detect, say, parts of a line. Here are edges. And essentially each layer learns more semantic information and it feeds into the next layer. And this is not exactly how it happens in a neural network. We don't actually know how it happens. But this is just to give you an idea of what it means for activations in one layer to cause certain activations in the next layer to fire, right? And this is seen throughout all of deep learning, where deeper layers will have more semantic information. So if I gave you a picture, let's say it was you're classifying if the image is of an image of a dog or a cat, right? The first few layers might pick up on edges. The next few layers might pick up on more details. And the last few layers will have the most semantic information, which you can make your classification based on that. So just to recap, this pattern here will cause the 9 to fire because it's a loop and a line. And if this was a loop and a loop activated and nothing else activated, then it caused the 8 to fire. So you can see how one layer, you can see how this layer depends on the previous layer. Okay. Now we're talking about the connections. So neural network. How are the neurons connected, right? Well, this is going back to the perceptron we talked about. Perceptron is just a single neuron, right? Well, go back. Well, this is the exact same thing, except we're stacking neurons. So in one neuron of layer I, you're taking the input from the entire layer I minus 1. You're taking the weighted sum of these neurons, just like a perceptron. You're getting these numbers, you're getting these activations, and you're multiplying each of them by a number. And these numbers are called the weights. So it's the weighted sum of the neurons, and this is W1 times A1, which is the first weight corresponding to the first activation. And you sum these together. Now, we want our numbers to be in a certain range. So we want our activations to say between 0 and 1. How can we do that, right? We can add a sigmoid function around our weighted sum. So that squeezes our everything into a certain range. Now all the neurons are between 0 and 1. Another reason for this is we want to introduce non-linearity to the neural network. As Rohan talked about before, you can model you can model non-linear functions to a high accuracy. And you can't do this without activations functions because right now it's still a linear relationship between the input and the output if you're only multiplying and adding stuff. But now when you introduce non-linearity, the neural network can learn any function to an arbitrary degree of accuracy. So one more thing. We have our sigma and we have our weighted sum, but what if we want the neuron to only fire or activate meaningfully when the weighted sum is greater than a certain number? This certain number will be called a bias. So if it's less than 10, it won't fire. But if it's greater than 10, then it will actually it will have a meaningful activation to it. And we do this just by doing minus 10 for the bias in the weighted sum. And yeah, if you're familiar with matrix multiplication, all of this can be put into matrix multiplication and you add a bias vector. So here you have the weights for all the neurons, in the previous layer corresponding to each of the neurons in this current layer. And you multiply that by the activations, and then you add a bias vector, and you'll get your you get one vector for all the new activations. So I'll go back and recap really quickly. When we look at this neural network, what's happening is you're getting your inputs and you're multiplying each of them by weights. You're getting a weighted sum for you're getting the weighted sum for each of the neurons in this next layer, and so on. And hopefully the goal is to have the correct weights and biases, or the best weights and biases, so that you get the right activations. And that leads me to how neural networks learn, talking about gradient descent, and how exactly do we learn the correct weights and biases? Because when we initialize those weights and biases, we initialize those parameters randomly, which means your input will get some random output, and it's not going to be doing very well at all. And so how does this neural network learn, right? We use a training set. And a testing set. So a training set is for the neural network to learn on. What it does is basically it makes a guess for one of the training set examples, and you adjust the weights and biases based on how wrong that answer is. And the testing images, so in machine learning, you have a training set and a testing set. The testing set is basically another set you like a smaller set that you set out to the side, and then you can test how well your network's doing. Yeah, you can test how well your network's doing. So like Rohan talked about, we know that the randomly initialized network is doing really badly. Like this is clearly not what we want. We want something closer to this, right? We know it's bad, but how bad is it, right? To get an accurate neural network, we have to first define what accurate means, and we have to know when the network is improving. So the same statement from the last slide, we adjust the weights and biases based on how wrong the answer is. How wrong is the answer? Well, you can use the cost function like you talked about. And in this case, we can use mean squared error, which is just take the difference and square them and take the mean of all the squared errors. And that's our cost function. So clearly, if this was perfect, you'd have all of these as 0 and 3 as 1 and the rest as 0. And then you have a mean squared error of 0. So you want the smallest error possible. Now the idea here is this cost function based on your parameters, you'll have a different cost, you have a different error, you have a different loss, right? Some parameters are better than others, obviously. And you can actually, you can say graph this. So let's simplify this idea to say our weights and biases, all these weights and biases are the parameters of a cost function. And let's simplify this to a single input. So let's say W, we had a single number for the weights, right? So clearly some number is going to do better than the other numbers. So you want to adjust your weights and biases based on how wrong the answer is. And to adjust these, like Rohan talked about, you want to go in the direction of the negative gradient, which is basically when you have your derivative, you want to go in a negative direction. So you minimize. So you can think of this as a ball rolling down a hill. So let's say we start off initializing W as 0, and this is our cost. Well, if we look at the derivative, it's a negative slope. I mean, right now it's a negative slope, which means we want to move to the right. And then if we test it again, we have a lower cost here. So that's good. And our goal is to keep doing this over and over again until we reach a local minimum. And if you're familiar with calculus and derivatives, just, imagine a ball rolling down a hill. Which direction decreases this most quickly? So in this example, we have 2 parameters instead of just 1. Instead of just W, we have 2. And it can move in all directions. So which direction will decrease the cost? And clearly you can imagine rolling down a hill. And the difference between these examples and what we're actually dealing with is that there's just a lot more parameters. So there's a 13,000 dimensional space. But the idea is still the same. You're trying to go in the direction of the negative gradient. And here is a good demonstration. Give me a second. I'll talk about this real quick. So you have your weights and biases here. There's 13,000 weights, right? Well, if you take the gradient of this and the negative gradient of this, you get certain numbers here. And what these mean are to decrease the loss or the cost, you should make these changes to your weights. If it's positive, that means you want to shift it, you want to increase it somewhat. If it's a large positive number, you want to increase it a lot. If it's a small negative number, you want to decrease it a little, right? And just over several iterations, you slowly roll down the hill. You take steps down the hill. And in this example, if I have a line, let's say I have 2 points like this. See how the line, this is the cost gradient. So the line is slowly fitting. And here we'll reach a minimum right here. The function is theta 0 plus I didn't mean to do that. If I have 2 points right now, we can fit it perfectly and get a cost of 0. Because it's theta 0, which is the first weight, and theta 1, which is the second weight. And our cost function takes these weights as the parameter and gives us the cost. Now, if I adjusted this, like let's say this was our data. Now everything will shift and we'll have a new minimum. And now it's minimizing this. So you'll see that with these training examples, we have theta can go in directions, and you'll get a certain cost. You'll get a cost based on our weights. Some weights are better than others. And the purpose and the idea of neural networks is just that over time and training, we'll learn the correct weights and biases. And effectively what this does is it becomes a really good pattern matcher. So it will start to learn that 3 or let's say the 9. You'll start to learn that this 9 will cause the correct activations here and the correct activations here, and ultimately the correct final activation. And over time, that's how we learn. Just adjusting these weights and biases. So this was actually if you want to review this and go more in depth, a 3 Blue 1 Brown has a really, really good playlist on this of what is a neural network and how neural networks learn. So we covered the first 2 things today. We did not cover the next 2 videos, which are what's backpropagation really doing and backpropagation calculus. So forward propagation is taking the inputs, you're multiplying the weights and adding the biases, and you're going through the network. Backpropagation is going backwards and actually making those updates based on the derivatives. And you can learn the calculus behind that too. So it's a really good playlist that I recommend. And that's it. If you have any questions, you can stick around.
Yeah, and I think next week we will do some practical coding applications of this. We might even do the handwritten digits thing, so I'll look forward to that. So if you guys don't have any questions, we are done for today. So thank you guys for coming, and see you guys next time. Okay, I think we are good. See you guys.